Very good. Thanks for being here. Happy Wednesday. Quiz 2 is due on Thursday. It's posted there on Learning Suite. Make sure you use the PDF that's posted for that quiz. Don't just do it by hand. That can throw the graders off. So you need to use the actual document there. Um, Test 1 is coming up next week, next Friday, not this Friday. Okay, so it's still a week and a half or so off there, but it will be over chapters 16 through 18. And to get started on 18, you can see the overhead here real quick. You see the electrophilic aromatic substitution reaction. Now we're putting things in motion here, right? We're making new products. All of these will go through this type of mechanism. You see the electrophile here, E+. We'll have to identify that from the specific reaction types, but they'll all follow this. The key to understanding this is to know what the true electrophile is. The reagents themselves, you won't always see that electrophile. But you'll see the different types of reactions. We've got Friedel-Crafts acylation and alkylation here to make carbon-carbon bonds. Those are probably the most important ones, the most versatile ones, because you can have any R group here or any ketone here. Nitration makes a carbon-nitrogen bond, nitro group, and then carbon-sulfur bonds from sulfonation, and then halogenation. So the specific reagents and the mechanisms we're going to go through. It's a little more complicated though. We've got some rearrangements here with primary, especially with the alkylations, and we can reduce the ketones with these conditions here to form the straight chain alkyl benzenes. And then the other difficulty here in chapter 18 is, of course, dye substitution. Once we have one group on there, that group affects the electronics of the benzene structure. It can make it more electron rich, make it react faster, and direct that second group to an ortho or a para position. If it's an electron deactivating group, electron withdrawing group, it'll direct that second electrophile, if we do another reaction, to the meta position. Okay, so we can get ortho, para, or meta, depending on whether we have a donor group, whether it's electron rich by resonance or induction effect, or by resonance it's electron withdrawing. So we'll have to look at the different groups and how they affect that. And a couple other reactions here to help us with synthesis overall. Okay, so that's how it looks for the outline for the chapter. Let's catch your attention a little bit with this. Okay, so go back down to the board here. Here we're taking benzene, something we get out of coal tar. We crush up the coal and steam distill it, and about 80 degrees C, the liquid benzene comes over. We can nitrate it and then reduce that nitro group to an aniline. So there's two steps to make an aniline from benzene. We can acylate the aniline and make the amide, the acid amide. That's electron rich enough because it has a donor group, the lone pair here. We can use sulfur trioxide, sulfuric acid to get the sulfonate. Okay, we can put on the sulfonic acid. We can take off the acetate and get this molecule right here. Now, this is one of the first antibiotics that was developed. It's called a sulfadrug. It was developed over 100 years ago to treat various infections. And it's still used in the clinic, actually. It's a simple material. It's fully synthetic. Oh, we need a proton there. In bacteria, it mimics PABA, which is para-aminobenzoic acid, which is a metabolite needed for the bacterium to make folic acid. Folic acid is essential for the life of the bacteria. We need to get folic acid on our diet. Okay, but this drug binds more tightly to folic synthase, so it prevents the synthesis of folate inside the bacterium. And you can see PABA is para-aminobenzoic acid. So you can see the structure here is very similar, right? This one just has the sulfonic acid in the place of the carboxylic acid. It has the same amino group, but this is the drug, and this is the endogenous substrate in the bacterium. But You know, the synthesis is the important thing, but I like to show you the applications. This eliminated a lot of problems. It was widely used at the beginning of World War I on the battlefield, actually, to prevent gangrene in the bad wounds. Maybe you've seen in some of those war movies, the medic shows up to the badly injured person, rips open a little bag, and dumps that yellow powder all over the wound. What is that? That's this. Okay, the sulfa drug. Anyway, let's look at some of the background issues here, getting into the mechanism. We'll do the general mechanism and relate this first to reactions we already know, right? And we did this before. We talked about aromaticity. Here's how alkenes react with bromine, right? Form the dibromide, okay? Well, can we do the same reaction with benzene? The answer is no, no reaction. We have to have bromine with ferric bromide. Then we get the mono. And what do you notice? We're getting the aromatic structure back, okay? We'll see what the true electrophile is here in a second. It's different than just molecular bromine with an alkene, and it gives a different product, gives the monobromo. This also works for chlorine as well. So what do we have over there? We had sulfonation, we had nitration. So, you know, and you got the review on the overhead there. But we'll go through them sequentially. And here's Friedel-Crafts alkylation and Friedel-Crafts acylation. So another couple of name reactions there. Let's look at the general mechanism of all of these. They all follow the same mechanism. And it's related to what we know about electrophilic alkene additions, okay? So hopefully this, you know, looks familiar, right? So some sort of HX reagent. Here's our electrophile, which is a proton, right? And we put that proton on there. We got a carbocation, right? And then what was our byproduct here, intermediate-wise? Oh, it was the X group, whatever that was, halide or whatever. Okay, so that's what we learned in chapter 9, I think, with alkenes. Notice the pi bond's gone. We went from sp2 hybridized to sp3 hybridized at the expense of the pi bond. That's only worth about 60 kcals per mole, and we get the new sigma bonds that are worth around 90 kcals. So that kind of helps remind you. And it's electrophilic addition. This is our electrophile. What electrons does it love or want? It wants these pi electrons, right? And so you can consider the alkene as a nucleophile, right? Okay, let's relate that to electrophilic aromatic substitution then. We got benzene, same thing. We'll leave the electrophile generic right now, okay? All 5 of these reactions will want electrons. Benzene's acting as what? The nucleophile, okay? It's looking for a positive nucleus that it can dump its pi electrons off on. Now, remember we said this is worth a lot of stabilization energy, 30 kcals per mole. So the electrophiles in this case will have to be more reactive, okay? And they will. You see some Lewis acids up there, the iron and the aluminum. Now, our reagent here, intermediate-wise, we could just bring this reagent on there, and that would be completely analogous to what we've seen before. But is that what we're getting? No, we're getting the mono product. We need to interrupt this intermediate and not do an addition there. Notice that would eliminate or remove the resonance stabilization energy. Instead, what do? We'll have some sort of weak base that can grab a proton instead. Now, this is the pathway. This is the new thing. Everything else to that point is what we've seen before, right? So if that can take that off, look, those electrons can come back down. And what do we get? We get a substitution reaction. Electrophilic aromatic substitution. Okay. Questions on the concept. Why does it follow this pathway now? Aromaticity, right? 30 kcals per mole, helping us out there. So that's the main difference. The other thing to look at here, resonance stabilization of that intermediate allylic cation. We can draw a lot of resonance structures. And you should be able to do that and recognize that now, because we're going to use that later when we get into dye substitution. Because if you already have something on here, that donor group or withdrawing group is going to affect the stability of our intermediate allyl cation. Okay. Sometimes it's called a pentadienyl cation. It doesn't matter. It's highly resonance stabilized. It's positively charged. It's higher in energy, but that's what it will look like. In fact, let's look at the energy diagram right now. So those intermediates, and we'll leave them up there. Here's benzene with some electrophile. Here's the energy. Here's where we start. We're going to go up to our pentadienyl intermediate, and then down to the product. The product is more stable than the starting material, so thermodynamically we're going downhill. But we're going uphill a slow step here to put on what? Put on the electrophile. So there's our intermediate. But you see, anything that's on the benzene already that might stabilize this allocation going to help us with a second reaction. Okay. But there's our transition state. So it could be lower there, or it could be higher. That's kind of the key thing for dye substitution coming up. And if you've read ahead, you can already see how that might work. And then what's this barrier here? Well, it's another step. It is a two-step reaction. That's where the base needs to take the proton off and regenerate the aromatic structure. So I like to show this early on to point out a couple of the factors that are coming up in this chapter. But any questions on that as we progress to the product? Factors that might be borne out there. All right, let's get into nitration. So we'll always draw the reaction, and that's the first level of your understanding, is recognizing the starting material, the reagents, nitric acid, sulfuric acid. Boy, you can't get much more corrosive and reactive than those two together. There's no water in there at this point. That's just the pure stuff. Be very careful with those reagents. Okay, very corrosive. Get any on your skin, you're in trouble. Okay, so these are very reactive. And what we're going to get for the product is nitrobenzene. Okay, and that's the second level of understanding in OChem, right? Reactivity. Starting material, reagents, what product. Forming a carbon-nitrogen bond. See, it's one of the steps there to make the sulfa drug. So you can see why it might be important. Changes the properties completely. This is a more polar compound now. It's still liquid. Nitrobenzene is still liquid. It's much higher boiling than benzene itself. So again, that's the magic of OChem. We change the properties as we change it to a new material. But how does it work? Let's look at the resonance structure, the full structure of a nitro group. Make sure you can draw that out, add in the lone pair electrons as needed, but it has two opposite charges. There's always a plus charge on that nitrogen, right? And you can draw a resonance structure of that, right? With the two oxygens trading, having the negative charge. Really, it's a molecular orbital with those shared equally over those. So how do we get there? The next level is mechanism. How are we going to do this? We need to identify what to figure this out. What do we need to identify here for the mechanism? Yeah. Yeah, nucleophile and electrophile. What is the true electrophile here? I already pointed out the nucleophile. The nucleophile is benzene. That's where the electron density is coming from. But how do we take nitric acid which looks like this. I think from Gen Chem, maybe you can remember that polyatomic protic acid, some of those there. And yeah, the resonance structures and Lewis dot and all that stuff applies from Gen Chem. But what do we do now with sulfuric acid? So we have H2SO4, and we've got an acid here, protic acid here, protic acid here. What are we going to do? One has to be a base, one has to be the acid. Let's take this and use that, the stronger protic acid, we could say, and protonate nitric acid. Nitric acid functioning as a base? Okay, well, if it's in the presence of a stronger acid, it can do that, right? And so what do we get? Get nitro and protonated OH. Now, that's the mechanism your book shows. They show that intermediate. They don't show the nitro group drawn out completely. They just leave it as NO2. I actually don't like this intermediate. There's probably some other pathways. You can actually do this by protonating this O minus and then losing water to get to the true electrophile. That's what we're trying to do, get to the true electrophile. What's a potential problem with this intermediate? We'll stick with it for the purposes of our class, but what might be a problem here? Anybody? First of all, we're using a strong acid as a base. That's maybe one. But what do you notice about this structure that might make it very high in energy, unstable? What do you think? Do you like two positive charges being right next to each other? No. Okay, a couple people saw that. But we can get rid of that. Let's bring the pair of electrons here and eliminate water. So what do we get now? We get N, O, and water. Am I done? Let's see, this oxygen becomes neutral, right? What about this nitrogen? Is there still something needed there? What do we need on that nitrogen? No, plus charge. Remember how we do formal charges, right? The number of valence electrons, which is 5, minus the number of bonds, which is 4, and then there's no lone pairs on this nitrogen. So it's plus 1, just like it started here, right? Here you see the 4 bonds here. Here the electrons came in, the electrons went out, so this nitrogen still has a plus charge. Guess what? That's our electrophile. Nitronium ion. That's the true electrophile. Okay. So we still haven't made a carbon-nitrogen bond yet. What do we need to do, though, with our benzene? We need to take our benzene and react it. Okay. So there's our electrophile actually going on. That will give us what? NO2, and I'll just abbreviate it there. NO2 is this thing, right? Okay, and that still has a plus charge. The electrons went in, the electrons came out. So all these intermediates, that nitrogen has a plus 1 charge. So I have this. Is that correct? No, we need a plus charge right there. Don't forget about that. Okay, for the mechanism, you have to be thorough there, keeping track of every pair of electrons. And we get to this point, what are we going to do? How do we get to there? We need what? We need a base. What base are we going to use? We got a couple here. When we take this proton off, what do we have? We have bisulfate. It's not a great base, right? We'd be going back to a very strong protic acid. What else do we have here that could be a base? Water. Now the book uses this. I would argue that as water builds up, that is a stronger base actually than bisulfate. Sulfuric acid, pKa is what, 4, -5, whereas hydronium ion protonated water is -2. That'd be a weaker protocast. So that means this would be a stronger base. Right? I'll let you use either one for the purposes of this class. So let's actually use the better base here. Okay, there it is. And look, that goes directly to the product. And hydronium ion, or back to sulfuric acid. Okay. Questions on the mechanism? The tricky part is this inorganic stuff right here, right? The stuff from Gen Chem, you could say. And then if you remember the basic mechanism for nitration, you'll see the rest of it there. Question on that one? Okay, you all right? All right, not bad. 1 down, 4 to go. Let's see. What's going to be our next one? I think sulfonation. So here's the basics of sulfonation. We're going to make sulfonic acid. We can just use H2SO4, or we can use sulfur trioxide and H2SO4. Sulfur trioxide is the anhydride of sulfuric acid. This will make a carbon-sulfur bond. Again, this is the pure stuff, no water in there. So what do we get? We get out the sulfonic acid. Notice it's an aromatic group now on the sulfur. So you could say we did a substitution on sulfuric acid. Or we just abbreviate it AR, and then SO3H. Okay. But benzene sulfonic acid is our product. So that's the first level of understanding, right? Second level in OChem, reactivity. What starting material gives what product? And notice what type of bond we're making? A carbon-sulfur bond. This is actually reversible. If we treat this with like HCl or HBr and heat, we can actually drive off the sulfur trioxide and all that. And that's because a carbon-sulfur bond is weaker, and this is a reversible reaction. I'll show you the mechanism of the reversible thing later, but let's see what we get here. Let's take sulfuric acid, and let's protonate it. So we'll kind of jump ahead in the mechanism. So we did an auto protonation, sulfuric acid with itself. And that's okay, you know, we're heating this thing up. We got pure sulfuric acid, so some of this is present all the time. And then what? If we lose water there, what do we get? We get the sulfur and that's called the sulfonium cation. Guess what? What is that then in the mechanism? That's the true what? Electrophile. There it is. Okay. A little easier to see. You can do the same thing from sulfur trioxide. We can draw it like that. Sulfur trioxide, what? If you just protonate with strong acid, you go from SO3 to this, okay? So the SO3 combination is nice. It's a little faster. You don't need to heat it up if you just have that. But if you just sow sulfuric acid, we'll let you generate the sulfonic acid product, okay? And there's our electrophile. So what's our mechanism here? We need to take benzene and attack. And what do we get? We get the sulfonic acid on there. So it's the hydrogen where the electrophile went on, right? And then your allocation. We're not drawing all the resonance forms. Those will be important later when we look at poly substitution. But there's our guy. And then what can we do here? We've got some bisulfate base. And as water builds up, we just generated some water here too. So we could have done it with water also there. Don't sweat that. That's not an important thing. Use water or the bisulfate and take that off. And then that collapses back down, okay? To give the aryl sulfonic acid product. Questions on that one? All right, let's try halogenation. So same reaction with benzene, electrophilic aromatic substitution, not a nitro group now. We're going to halogenate, and we're going to need bromine, Br2, and ferric bromide. Not ferrous, this is ferric. Remember the difference between those two names, ferric versus ferrous? What are we referring to there? The charge or the oxidation state? Yeah, so ferric is the +4 oxidation state of iron. Iron can be in a couple different oxidation states, including +2 is the other common one. But this is the halide form of iron. It's a Lewis acid, meaning it has an empty orbital here. So Lewis acids are electron pair acceptors, right? Okay, Bronsted bases are hydroxide providers or proton acceptors, right? And a proton H plus is really just an electron pair acceptor from a base. So a proton is still a Lewis acid, and it has an empty orbital, the 1s orbital empty on H plus, right? Here your empty orbital is a d orbital, and don't worry about which one, but we'll use that in our mechanism because we can't see what the electrophile is. That's what you should be keeping straight here, along with the reaction, right? And this works for chlorine also, so Cl2. And then you switch over to ferric chloride. You can actually mix up the halogens and it'll still work, but use the halide here on iron that corresponds to the halogen molecule. There are other Lewis acids that will do this, but we'll just stick with the ferric bromide or chloride, okay? We won't do fluorine. F2 is too reactive, it's explosive, and iodine's not reactive enough. Carbon iodide bonds are too unstable. But what are we going to do here? Let's take a pair of electrons here and dump them in there. So we'll have this adduct here. Let's see, what is that going to do? This lone pair right here just came out of that bromine molecule. We need some charges here. Okay, I just went ahead and added them for you. And you can do the formal charge thing here on bromine, right? It's what, 7 valence electrons minus 2 bonds, and then you have 4 lone pair electrons. So I think that's +1. Yeah, that's still okay. And iron goes to ferrate, negatively charged species, because it has another bond on it. Wait a minute, metal as a negatively charged thing? Yeah, it's okay. Depends on what ligands or what groups are on the metal, but that's okay. This is actually the true electrophile. Well, that's different than just Br2 on its own, right? And how is it different? This middle one is electron deficient. So it's pulling more on these electrons, right? Which makes which bromine the one that's going to react with benzene? Let's see if you can guess. Is this bromine on the end going to jump onto benzene now? Or is this one in the middle going to jump onto benzene? Who says the one on the end? A few, okay. Who says the one in the middle? A couple were saying that too. Let's see. This one, as it pulls on these electrons, what's it going to do to the electronic character of that end bromine? And which one sterically is more available? Yeah, this end one. So let's see. Let's push the electrons just like that. You see that by complexing with the Lewis acid, it renders that bromine on the end more electrophilic, more reactive, more susceptible to attack there. So you see why that soups up the reactivity. Bromine on its own without the Lewis acid is not electrophilic enough to attract the pi electrons out of benzene. But when you coordinate it, you see the plus charge on this middle bromine makes this one partially positive too, right? As it breaks that bond. And that's the flow of electron, which will make this bromine then neutral, okay? Well, let's see. Let's see what the intermediate looks like. So we get this. the bromine on there, H. And what's the rest of the deal here? FeBr3. And we need a negative charge there, right? Okay. So there you go. There's the complex now with 4 halogens on iron. So it's now an 8 complex. It's ferrate, we say. And here's our intermediate, which looks just the same, that allylic cation. Now we need a base. That's kind of the tricky thing. We don't have bisulfate. We don't have nitric acid. We don't have water. What's going to be our base? Do you see anything that might grab? Here, I'll give you a hint. The reaction does become acidic. HBr begins to build up. You need to neutralize that when you isolate the bromobenzene. So what is it? What's going to be our base? Well, it's right here. So let's just take these electrons out, grab that, comes back down, okay? And that generates that. The pKa of this intermediate is very low. It's estimated to be, I don't know, like 2 or 3 or something like that. And then you add on the aromaticity factor, which can make that very fast. That step's very fast. This is the slow step here, right? This step's fast, let's say. Okay, questions on this? So you can do it with chlorine, make chlorobenzene, similar fashion. Okay. Yes, please. I'd say +3. So yeah, iron. So yeah, if you wanted to keep track of that. So yeah, it's bonded to 3 other atoms that are more electronegative. So you don't see a +3 charge. It's actually not a salt. It's actually a covalent compound. But it is Lewis acidic, like a lot of metal oxides and complexes. But yeah, it's used as a Lewis acid. We'll see some other Lewis acids here in a second, aluminum. The question on the reactivity or the mechanism, I think that's okay so far. All right, what's the next one? Friedel-Crafts. Friedel was a professor at the Sorbonne University in Europe. What city is the Sorbonne in? Any Francophiles out there? There's a hint for you. The City of Lights. Where is Sorbonne? Paris. Okay. So the city of Paris, famous university, very old university. Friedel was a German scientist working in France, and his research assistant was James Crafts. So that's why we call it the Friedel-Crafts reaction. James Crafts was an American postdoctoral fellow working in Europe to finish his training. He went on to be a professor at MIT in Boston and brought a lot of this technology to the United States. This reaction, the Friedel-Crafts reaction, is considered to be one of the most important industrial reactions we know because we're converting benzene out of coal tar, simple material. We can make a carbon-carbon bond and put on ketones or alkyl groups of any kind. That opens up a huge range of materials. Okay, so that simple idea that we're going to talk about has profound influences on things. So let's look at this, the basic reaction here for Friedel-Crafts alkylation. We'll do first. So here we'll have a specific one, a new Lewis acid. So this is tert-butyl chloride and aluminum trichloride. If you don't have the Lewis acid, no reaction. You need to have the 2, okay? And then when we do the 2, what do we get? We get tert-butyl benzene. Now you might think, well, big deal. Okay, well, it goes up in molecular weight, has very different properties, and these branched hydrocarbons, these smaller ones, tert-butyl benzene and cumene, the isopropyl benzene, that's aviation fuel. That's a high octane fuel. And we really needed that after World War I, and especially for World War II. This Friedel-Crafts reaction was a key component for aviation fuels that the Allies had. The British and the Americans had this technology, able to scale it up. That's because Crafts came back to the U.S. was able to do this on large scale. So we'll see the implications of that. But it works for bromine here. It works for primary, although that's slower than secondary, slower, and tertiary is the faster one. So that kind of gives you a key here of how this thing mechanistically is going to work there. But it's very versatile, okay? So tertiary and secondary are the better ones. Primary a lot slower and actually a different mechanism. I'll have to modify the mechanism a little bit for primary. So this already tells you what we might have to do here. So there's our Lewis acid with an empty orbital, right? Let's add that in there. And what do we get? Chloride, aluminum, aluminate, and chloride with a plus charge. Keep track of those formal charges. That's not the true electrophile. That's an intermediate. Okay. This mechanism is a little more complicated. So what do we do now? Break that bond. Why are we breaking that bond? Well, it's tertiary or secondary. And what are we going to get? What's the true electrophile going to be? I think you can already tell, right? What is it? What's the true electrophile going to be for Friedel-Crafts alkylation? What's generated by breaking that bond? Yeah. Tertiary carbocation, yeah. So somebody identified the charge on it. It's going to be a cation. And tertiary, you can already see from the kinetics which one's faster there. So let's break that. What do we get? There's our tertiary carbocation. We know that to be a stable guy. And then our aluminum chloride. And I'll keep drawing it like that. I could just draw the 4 chlorides on there and the negative charge on the aluminate, but that's okay. And then what? We need to have benzene attack. Okay, and that will give us our same thing here, the allyl cation. Okay, and we need what now? So the mechanisms are all the same. Put the electrophile on, and then we need some sort of base, right? To take it off. What's the base in this case? It'll be chloride coming off. And yeah, these do get acidic also. Generate the product plus HCl. And the Lewis acid is there to go again. Questions on that mechanism? So I think you can see with secondary, that would be a similar deal. If we did this reaction, say, with isopropyl chloride and aluminum chloride, what would we get? We get the secondary carbocation. Be a little bit slower, but that would be our electrophile. And what would be our product here? It would be cumene, isopropyl benzene. That's the high octane aviation fuel, actually. Okay, let me give you a little quote from the end of World War II. There, who was the Prime Minister of Britain during World War II? Winston Churchill. At the end of the war, he had a famous quote. He said, well, part of it, never before in the course of human history has so much been owed by so many to so few. The so few he was talking about were the brave pilots in the RAF, the Royal Air Force, who fought off the Nazi Luftwaffe, right? But they also had higher octane aviation fuels, and they had that radar system. So if you know something about World War II, technology played a major factor, not just the heroics of the fighters, but here's one of the compounds. One of the few is right here, cumene. Let's look at the primary version here. You can do this reaction with primary Friedel-Crafts. In fact, you can do it with methyl or ethyl. Let's see the two here. So methyl iodide, and you need aluminum chloride, and you can get toluene. Okay, so there's a reaction for you with the primary. Very simple one. You can do it with ethyl chloride. Make sure you have the aluminum chloride there. That will give you the ethyl benzene. Okay. So how do these work? Well, it's the same complex, same idea here. The aluminum coordinates a lone pair on the halide and CH3. Now before in our mechanism we did what? We broke this and we had a carbocation. And it was more like an SN1 type reaction where we ionize first through a carbocation. But now this is primary here, right? So this is actually reactive enough now to react directly with benzene. So this is the true electrophile if it's primary. Okay. No carbocation. Why? Because that's much higher in energy. It's not free like that. And plus it's a combination with the sterics being smaller. So this can attack directly. Give us what? Same intermediate. There it is. And then halide. Coming in here and take that off. That gives you the product. Okay. So very similar, but different. Okay. Here's the next thing to be worried about. What if you have a primary that has branching, or a longer chain than ethyl, let's say? If you have a chain, it's going to be a little bit longer. And let's see, which one should we do? Okay, this one. In fact, that one will have some branching to it. Yeah, that will do Friedel-Crafts alkylation. It's primary. Those work. Okay. But guess what? This actually is a product. Let me see. Do I have these numbers here? Where is it? Oh, this one, in this case, you get a 0% yield of that one. You get a product, though. It's not that. Instead, it's this. This is the true product. Tert-butylbenzene again. In fact, you get this in a 92% yield. And that's not a typo. I didn't make a mistake here. This guy here, which is sec-butyl chloride. I'm sorry, isobutyl chloride. It's primary. Isobutyl chloride reacts Friedel-Crafts conditions to give tert-butyl benzene. Why? Well, let's examine the intermediate. Let's see, chloride, complex to aluminum. So normally we would think, well, we just attack right here, right? And now this is a little slower because our nucleophile would have to attack past that isopropyl group on the end. What can occur here to give us the true electrophile, what does it have to be? It has to be tert-butyl cation, right? So what can we do here? Let me help you out a little bit. What occurs here? Somebody kind of gave the hand motion like that, or so mechanistically you could probably figure it out. What do we need to do here? Hydride shift, very good. And we saw that before with some SN1 reactions where we had primary or secondary carbocations. And remember, 1,2 shift can either be a hydride or an alkyl shift. In this case, the person identified it as a hydride shift as that bond breaks. So here's the rest of the mechanism that rationalizes what's going on here. By doing that, you see we get this hydrogen over here now. There's now 3 hydrogens right here, right? I won't draw that all out, but then chloride comes off on the aluminum, just like before, and we'll draw that one chloride out there. And then what? Benzene can do its thing. Tertiary carbocation now from that primary chloride. Now the attack. And then I think the rest of the story there, we got an intermediate and then the base again. Okay. So the bottom line here with primary, okay, primary, we get shifts. Now with methyl and ethyl, we couldn't get a shift that gave a more stable thing. But look, with propyl, what would happen with propyl? What if we did this? Benzene. Sorry, I'm kind of emphasizing the new substrate now. Normally we draw the benzene as the starting material. Doesn't matter, right? We use this. What product are we going to get now? Yeah, we're going to get isopropyl. We get cumene again. Okay. Question on that. Yeah, so if it's primary, Can get hydride or an alkyl shift, okay, depending on what we need to do to give the more stable carbocation. And that's kind of the key to figure that out. We saw that before with SN1 reactions and some other rearrangements that involved intermediate carbocations. We avoid the primary at all costs and do a shift there if we can. Okay. Let's look at other types of electrophiles. Now, these are still called Friedel-Crafts reactions, but instead of halides, we're going to use sometimes simpler type of electrophiles. We're going to do cyclohexene with sulfuric acid. And we're going to do, how about this one? And this kind of combines a couple things. An alcohol with a Lewis acid, BF3. Wow, these are going to be a little bit different, but let's do the mechanism and see if we can figure these out. So if we have a strong acid with an alkene, what do? We do this, right? We protonate the alkene. And we saw that before, way back in chapter 9, right? And that'll give us this. Secondary cation, that's okay. And if a secondary cation sees benzene, what's going to occur here? Oh, Friedel-Crafts. These are still called Friedel-Crafts reactions, even though they're not halides. So what's the product in this case? Well, it's cyclohexyl benzene. So we could have made that from cyclohexyl chloride or bromide, but the alkene is actually cheaper. And so a lot of times we'll do Friedel-Crafts directly from that. And we always protonate in such a way we get the more stable carbocation. Okay, so it's that Markovnikov protonation you need to remember there. Okay, what about this one? This is 1-butanol. Lewis acid. It's going to react, but look at this. The major product in this case is sec-butyl benzene. How did we isomerize over into the secondary position? Can you figure out the mechanism? Yeah, sorry, we're almost out of time. Let's see. Let's bring that in there. What are we going to get? We're going to get a Lewis acid complex, which is what we've been doing with the halides, right? The aluminum and the iron, you go back to halogenation. That looks kind of funny, right? But it's like a hydronium ion. The Lewis acid's like a proton there, right? And then what can occur? This can come off, right? Fully ionized off. But that would be a primary position. So what's going on here? The shift idea again. Hydride shift. So that will give us what? Secondary carbocation. And then we're off to the races, right? You can see how that will generate then the Friedel-Crafts alkylation product. All right, we'll do a little bit more on alkylation next time, and then we'll finish with acylation. Believe it or not, we've done 4 reactions. Acylation, I expect you to know here, and you'll need to know that for the quiz. You can read ahead there. I think quiz 2 is okay. We have a acid chloride there, and it forms the aromatic ketone. Make sure you pick the right one, the right R group for that question on the quiz. But there's other quiz questions that involve the 4 we just covered today. So I think we'll be okay on that. And the TAs will help you tomorrow in recitation to figure these things out as well. So you okay? We've done 4 out of the 5. Not so bad so far. Okay. Look for the commonality. Look for the true electrophile and relate that to the similar type of mechanisms. There's a couple things to worry about though, right? The rearrangement issue. That's probably the key thing, but it's similar to what we've seen before. So it should be okay. So yeah, we'll do acylation next time, and we'll get into dye substitution, okay? So be reading ahead in chapter 18 there, and we'll see you next time. Thank you.